Okay, so we've covered the basic premise of statistical mediation and some of its limitations, but what actual analysis procedures does it involve? Is it just about fitting these three linear regression models and then interpreting the results, knowing the fundamental theorem that A times B equals C minus C prime? Well, sort of. But there is one more key thing. We need to estimate the magnitude of the indirect effect A times B, and we want to know if it is larger than would be expected due to chance alone. We want to be able to describe our estimate of the indirect effect using a confidence interval. Confidence intervals for regression slopes are very easy to calculate, but this is not just a regression slope. It's the product of two slopes from two separate regression models. Some of the assumptions that go into making the most typical default kind of confidence interval are definitely violated in this case. The sampling distribution for the product of these slopes is not even symmetrical. Long story short, we need a robust way of getting a confidence interval, and we can't algebra our way out of this one. The modern standard technique for estimating indirect effects in psychology is to use bootstrapping to obtain a confidence interval. Bootstrapping works like this. You have a sample of observations and some statistic you'd like to calculate, such as the indirect effect. You need to figure out how far off you're likely to be when you calculate that statistic. So you need a way to describe a distribution of possible values that statistic could take on from experiments like yours. You randomly create an alternative version of your sample, with some observations duplicated and others removed, but the same overall sample size. That is called a bootstrap sample. You calculate your statistic in that bootstrap sample, in this case by fitting the regression models again and calculating the indirect effect again, and store that estimate. Then make a new random bootstrap sample, calculate the statistic again, and store the result. Repeat this several thousand times. Then look at the distribution of all the alternate versions of your statistic and use it to figure out how common it would be to obtain estimates much higher or lower. In this quick example, I have a sample of 5 observations, and I would like to bootstrap the mean. Each of my original observations is represented with a shape on the screen to make it easy to see what happens when I duplicate them in bootstrap samples. The actual mean of the sample is 3, not hard to calculate. Each bootstrap sample is made up of observations from the original sample, and each bootstrap sample has the same sample size as the original sample. But they're not identical to the original sample because the observations are randomly drawn with replacement, so they can end up getting included more than once. This creates a huge set of possibilities for the composition of the bootstrap sample. In this example, the first bootstrap sample has the 4 circle included twice, but it's missing the 1 triangle. The second bootstrap sample is missing both 4 and 5, and so on. These bootstrap samples give a sense of how the mean would vary if the sample were composed of different elements in the first place. And when you have large numbers of bootstrap samples, this principle can be used to construct a confidence interval for the mean, or for anything else that you can calculate in each individual sample. Let's move on to R for a more detailed illustration.